All right, Math 152 students, it's Rochelle again, and I've created yet another example, example 9 from section 6.2b. You will notice it is the same exact region, so I'm going to draw the region once again. Try to draw it nice and big again. So we have e to the x plus 2, which is going to look somewhat like this. We have x equals 0, or y equals 0 here, x equals 0 here, and then also x equals 1. I'm going to put it right over here. So again, this is the value 1 for the x-axis. This happens to be the value 3 on the y-axis. Now this is an interesting one. I hope to do maybe 2 examples here. But this one is revolved around x equals 1, and that is this vertical axis right here. So if we look at this axis, what we're going to see is when we try to revolve this, so I'll go ahead and revolve this, this is going to come over here and this vertical line is going to be over here. We're going to have a solid. This is actually a solid here. Kind of looks like a top maybe. This is a cylinder down here, and then this is a curved tip, a point, maybe like the top of a pencil or something. Now, in order to slice this, we're going to have to slice it with the dy. But what I want to point out is, if I slice it up here, oh gosh, that really doesn't look like a circle. So I'm just going to fill it in. If I slice it up here, it should really be, down the middle here. Versus if I slice it down here, my radius is going to be a little different. Down in this region, my radius is literally just going to be equal to this value of 1 right here. So I'm going to have to set up for this one, which makes it interesting, is I'm going to have to set up 2 integrals. One that goes from 0 to 3, and this is just going to be a disk. There's no hole in it. So I'm going to have radius squared. This is going to be, since I've sliced it this way and my thickness is right here, it is going to be a delta y. Especially when I rotate any time around a vertical axis, the slice is always going to need to be a dy for disks or washers. So this is going to be a dy. And these are y values, y 0 to y equal 3. Now I'm also going to need one from 3, and I'm going to have a radius squared again, dy. But now I'm going to have to find this point right up here. And that y value is going to happen at x equals 1. So all I'm going to have to do is I'm going to have to take my e to the x plus 2, and I'm just going to have to plug in the value of 1. And so that's going to end up being e plus 2. So this value up here will be e plus 2. So the trick now is to find the radius of each of these 2 different disks. Again, the disks along here are all going to have a radius of just 1. So my very first one here is just going to go 0 to 3 of pi times 1 squared dy. This one is going to go from 3 to e plus 2 of pi. Now I'm going to have to think about what this radius is going to be. So what we can do is we can look and we can say, okay, this distance right here is a distance of, because this is 1 down here, 1. This distance right here is an x distance to this curve. So I would need to take this function right here and solve it for x. So I'm going to subtract that 2 over first, and then I'm going to have to take the natural log of both sides. And I'm going to end up with the natural log of y minus 2. So this distance right here is equal to the natural log of y minus 2. But I'm looking for this radius, right? I didn't want that to be. So that's going to be the green minus the red. So realistically, my radius is actually going to be 1 minus, and then it has to be this x distance, which was the natural log of y minus 2. So I didn't really need an extra set of parentheses around there. So if I, whoa, excuse me. Stop. Stop. excuse me, I do not want you. I do not want wriggle cinemas or anything like that. Thank you. So this, I can bring the pi out in front. This is just going to be 0 to 3 of 1 dy. That's not very exciting. I could also bring the pi out of here. In order to complete this problem, e plus 2, it's going to be 1 minus the natural log of y minus 2 squared dy. I'm going to need to use my calculator for this. Since this is a constant, this is just going to end up being 3. So 3 pi here. Plus, this is going to be pi times some value I'm going to get when I plug it into my calculator. But I don't really want to spend my time doing that. I wanted to, let's just, instead of find the resulting volume, maybe we can just set up the integrals. Okay? So that would be this right here. Now I wanted to just mention, what if this had been revolved around the axis? So let's just try this again. Draw this little picture. I'm going to go ahead and draw it kind of small over here. I'm going to have the top. Oh no, I can't do that. I'll just slide this down. Wow, I don't know what happened there. Here's my 1, here's my 0, and so on. What if I had revolved this around the axis x equals 2? So if I had done that, I just wanted to kind of mention this. What would happen is I'm going to end up with the same exact situation, except now I can look back over here. These are the equations for just discs. Now I would have the equations for washers. And they would need to be sliced here again between 0 and 3 and between 3 and e to the e plus 2. But I'm just going to have a hole in the middle. And hopefully you can see that my inner, when I slice it down here, my inner radius is always going to be, since this is 1, 1, and my outer radius is always going to be 2. Up top, whoa, my inner radius is still going to be 1, but my outer radius is here going to be exactly what we did before. My inner radius here would be it would look just like this, except it'd be 2 minus that value instead of 1. Now I know I did a lot of that verbally, but I just wanted to kind of give you an idea of that it could be done by other axes. All right, that's my last video for the evening. Enjoy.